So the only case in which you actually cannot walk forward is a problem like this. In which I really start at the tail. So say that I have a bar like that. And let's say that X starts at the end as well. And this is section B, and this is section C. And I'm giving you the very end of the story. Ux of X equal to, let's see what I have here, Bx that multiplies 2 minus 1/3 x over L square. So you're given Ux of X, and you're also given A, E, and L, the geometry and material of the bar. And what I want is what kind of loading? What kind of loading is going to give me that displacement field? So somebody comes to you and said, I had a camera there, I looked at this bar, and this is the way it displaced. That's all what I know. I can tell you what material it is, I can tell you what geometry it has. I have no idea what's causing this to happen. Tell me what loads are on the bar. Okay, so in this case, because you have no idea what the loadings are, there is no way that you can go forward because you cannot do the diagram of the forces. You have no idea what n of x is going to look like going forward. So in this case, you really need to go backward. So this is really a backward problem. Backwards. It's not hard. You just have to do some derivatives, but you're good. So by knowing, yes?
Yeah, sorry to interrupt.
No, you always, very clear thing. I love when you interrupt me, because when you interrupt me, it means I forgot something or some. If you have a question, everybody else is going to have the same question. So never be sorry to interrupt me. Just cut me dead. Just go.
Okay, not sorry to interrupt. 2 minus, what is that? Is that 1/3x?
Yes, it's 1/3. Minus 1/3 x over L squared. It's just a function. Somebody came there, look at what happened, and tells you it's minus 1/3. Just bad handwriting. Okay? All right. Oh, by the way, units. I always like it when you and I put things grouped nicely for units, right? So if I have x and L, I like it when they're together so that I know this is dimensionless. And Ux is a displacement, so it's a length. So since x is a length, I already see from this equation here, does B has any dimensions? B is dimensionless. Okie dokie. So let's go forward. Let's go backward. I can walk backward. So if I have Ux of X, what can I get from Ux of X? Straight. I can differentiate it. I can say that epsilon A of X is equal to dux dx. No problem. Let me write this thing as, so if I do that, that's equal to 2bx minus b over 3 L squared. Actually, let's do minus b over L squared x cubed over 3. All right, so I can differentiate that. That gives me 2b minus 3 and 3 cancels out, minus b x squared over L squared. I like to group it, so that's going to be equal to b that multiplies 2 minus x over L squared. That's nice. So epsilon A of x is that. And let me write it that way so that I can do a plot of it. Epsilon A of x. Okay, so my epsilon A of x, when you plot it, just ask yourself, how much is it at 0? How much is it at L? Does it go up with x? Does it go down with x? Is it linear, right? So that's the thing you do when you plot it. So how much is that at x equals 0? Well, if I plot epsilon A of x like that, at x equals 0 is simply equal to 2b, right? So I start from, let me do this one a little lower. So I start from 2b at x equals 0. And then when x is equal to L, that's 1, so that gives me b. So this goes from 2b to b at x equals L. It goes quadratic and is going down. So it's going to do like that. Good? So that's my epsilon A of x. OK. So after epsilon A of x, I keep walking backward. So epsilon A of x, what can I do then with epsilon A of x? If I know the modulus of the material, what can I get out of that? I have A of x, it's A. But with A, I can get n of x. To get to n of x, I need first to get from strain to what is related to n of x. I can directly get n of x from my good old friend, because I can say epsilon A of x is equal to n of x over EA effective of x. And EA effective of x is simply equal to EA. So I can get that my n of x is equal to EA times epsilon A of x. So EA then multiplies B, then multiplies 2 minus x over L squared. Fantastic, I say. And the nice thing is that I do not even need to make big effort to get an n of x plot. I can say n of x is equal to a plot that looks just the same as that. And it starts over here with 2b EA, and it ends up here as b times E times A. Right? Brilliant. The intermediate step that I was looking for, and in this case is not that important, is to go through stress. Because from epsilon A of x, if I want, I can go to sigma n of x equal to E epsilon A of x. And sometimes, if one of the things that I ask you has to do with stress, like for instance, I tell you, this is the displacement field, what is the stress in the steel, or in the aluminum, or in the core, or in the sleeve, there is an extra step there that tells you once you know the strain, you can get the stress in any material if you know the modulus and the strain. Okay? In this particular problem, because my final destination is the loading, I don't even need to go through the sigma n, because I really am not interested in the stress in this problem. I'm interested in what is loading the bar. So I can directly go through this step over here and find directly my axial force resultant. Okay? So that was good. All right, what do I do with n of x? What do we start from? Then normally we start there and then we get n of x. We get what? Fx. So remember, the thing that normally we go down, we can go backwards. So we can say dn dx is equal to minus fx of x. Right? That works. So I can take this one, I can differentiate it, and I get, so I have minus EA over L squared, and then I have another minus 2x. And so the minus and minus cancels out, and I have B, and the 2 and 2 cancels out, so I end up with x. Okay? So my dn dx, my fx of x, is simply EAB L squared over x. So I can plot it out. And it goes like that. And the maximum value is 2AE. Did I screw up something? That should be 2AEB. There is a 2, correct? Sorry. OK, so 2AE over L squared B. OK, so now I have the fx of x. Am I done? I am not done, because you see at the very end here, I had an axial load that was not 0. You see that? I have an axial load at the very end of the bar, right here, that is not 0. How does that work? If I look at the very end of the bar, I take a disk at the very end of the bar. These equations here tells me that my axial load at the end is something, is not nothing, is BEA. If I take a slice at x equal L. So how can that be? Something must be pulling on that end of the bar, because otherwise I cannot have a non-zero axial load, correct? So something must be happening on this end, and this something, it must be a concentrated load that happens at this end FC. And if I do sum of the forces x equals 0, on that simple diagram there, I get that my axial force at the end of the bar must be equal to B times E times A. There is no way around it. So my final destination is that my axial loading on this bar was a distributed force that is linear, like the diagram shows, plus a concentrated load BEA at the end. Yes?
For the function, when x is equal to L, shouldn't there only be L to 1 power?
Oh, yeah, sorry, because that cancels out. All right, sorry, thanks about that.
And then can you just, say that very last part again?
Absolutely. So what I'm saying is that once you look at the diagram of n of x, the slope of the diagram tells you the distributed loading, right? So see no slope up there, and then big sloping, the slope increasing, that gives you the distributed loading. If you find that the diagram has a step here, remember a step here means I went up here on the diagram from nothing. There must be a load that brought me up there, right? So a way to figure out this load is I go there with a knife, zip, 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 zip. I take a small slice right at the very end, and I say, if I had an axial force here that was not 0, it means somebody was pulling on the bar. Otherwise, I cannot have an axial force different from 0. Who's giving me this axial force? Where does it come from? Right? So how much must this axial force be? It must be equal to my axial load, right? It all kind of comes together. Are we good? All right, sorry about the algebra thing here. Okie dokie. So this is the very special case in which you do not go forward, you go backwards. OK, do you guys have any more questions on this problem here? Yeah, do you kind of have a handle now on how to do these problems? You're going to have some problems, some homework problems you're going to do on your own. There's going to be example problems on Stellar For this kind of procedure, you can look at the example problem. You did recitation on Monday, which I hope helped, right? So you have recitation. You have an additional recitation problem online. Just, if you are in doubt, look at your example problems. Go back to your class notes. I'm going to post all these notes without algebra mistakes online today.